Hello, calculus students. This is Mr. Allen. Today we are going to look at an application of differential equations, namely the logistics equation. Now, we have skipped over section 5.2, which is on exponential growth and decay. We covered that last year, but that's more of a pre-calculus topic. We just derive it in calculus just to kind of show you where it comes from. So today we're going to see just two examples, and they're actually both pretty involved. So our objectives are to solve and analyze logistics differential equations and use logistic differential equations to model and solve applied problems. So when we looked at exponential growth model that was derived in section 5.2, that was the rate of change of the variable y being proportional to the value of y. You observe that this differential equation dy dt equals ky, which has a general solution of y equals ce to the kt. So this was the formula that, again, we would have used in section 5.2. Exponential growth, though, is unlimited. In other words, if we were to graph any exponential function, assuming that it has a positive, and it shouldn't hit the x-axis there, assuming that the c value here is positive, I guess it could be a decay model, but let's talk specifically about growth. This goes towards infinity, and as we know that basically you can't have an infinite number of anything. Like, so let's say we're talking about bacteria. You know, bacteria can grow quickly, but it can't just tend to infinity. So this is a good model, but it may not be the perfect model. So another model that we have, which is the topic of today's lesson, is the logistics model. This upper limit called the carrying capacity, which I hope you're familiar with from perhaps maybe one of your science classes, maybe biology. This is the maximum population that can be sustained or supported at some time t as t increases. The model for this is based on this differential equation here. So dy dt equals ky. So this looks actually very similar. It's exactly the same one we did for the exponential model. But now we have this. So this factor here, y equals y over L, that's going to give us that carrying capacity that we want. For the equation, you can see that if y is between 0 and the carrying capacity, then the growth is going to be greater than 0. That's what this is saying. And of course, if it for some reason you actually had more population than the carrying capacity, then obviously the growth is going to be negative. In other words, it's going to pull it down. The general solution for the differential equation is going to be derived in the next example. And this is going to take me some time, but I'm going to walk you through it because I just want you to get an appreciation for solving this, and I want you to see that this equation that we're going to use didn't just fall out of the sky. So let's go ahead and get started. So the first thing that we need to do is we want to get our t variables on the left side, and we want to get our y variables on the right side. So we're just going to do that by multiplication. So we multiply the right. I'm going to leave the k term there and put dt to the right. So I move the dt to the right. And now I've got to divide over this other stuff. So this is going to be 1, or y, quantity 1 minus y over L. So now we have separated our variables. So now what we'd like to do is we would like to integrate. Now the right-hand side is very easy to integrate. If we integrate the right-hand side now, we're going to get we're going to get kt plus c. And that's not a big issue. Let's see if I can erase just that little spot there. Good, there we go. The left-hand side, that integral is a little bit nastier. In fact, I'm going to do this in blue. And in order to integrate this right-hand side, we're going to have to use a technique called partial fraction integration. Now, I haven't taught you partial fraction integration. We will actually learn about it when we get into chapter 7, but I'm going to go ahead and show you it today. So before we actually do the integration on the left, I want you to consider the following fraction, which is what we have. 1 over y times, and then I've got 1 here, minus y over L, okay? That could be rewritten as 1 over y minus y squared over L if you distribute the y. Furthermore, we could say that this is 1 over y times L minus y squared over L if we get a common denominator of L. And of course, when you take 1 divided by a fraction, then you can just multiply by the reciprocal, so that fraction then becomes YL minus y squared. And so now my hope is that you can see that from here to here, things look a little better, okay? We've still got a little bit more work to do. And what I'm going to do now is I'm actually going to factor out a y on the denominator. So that's going to give me y quantity L minus y. Now we're going to start doing this partial fraction, and I'll do that now in purple. I claim that this fraction can be rewritten as a constant. Now, L, remember, is a constant, it's the carrying capacity. I'm going to say that this fraction can now be broken up into the sum of 2 fractions with the following denominators. So I'm going to write that as A over y plus B over L minus y. Now, how are we going to figure out what that is? Well, what we're going to do is we're going to use this equation right here. Now, I'm going to just do some algebra. The common denominator here would be y times a quantity L minus y. So if I multiply through by that denominator, on the left-hand side, everything cancels in the denominator, and you'd be left with just L. On the right-hand side, the A over y, well, the y's are going to cancel, so you'd be left with A times the quantity L minus y, plus, when you get to the second fraction, the L minus y's are going to cancel, and you'll be left with B times y. Now let's go ahead and do the distributive property, and we get AL minus AY plus BY. Now what I'd like you to notice is that this term right here is the only term that has L on the right-hand side. The right-hand side consists of AL minus AY plus BY. The second 2 terms on the right have Y's in them. So if I write a 1 right here, and then I just look at this first 2 things, that would be 1L equals AL. What does A have to be? Well, of course, A would have to be 1. Now, if A is 1, now let's consider these 2 terms. Let's do it in green. Let's consider these 2 terms right here. If A is 1, then you've got negative y, or I'll write negative 1y, then plus by has to equal 0. So then what does b have to be? Well, you'd get negative 1y equals negative by. So therefore, b is also going to be 1, positive 1. In other words, this fraction right here, a over y plus b over L minus y, can now be rewritten so that a is 1, so I'm going to make a 1 right there, and b is also 1. Now, if you don't quite trust me on this, this is the technique for partial fractions. If you don't trust me on this, simply get a common denominator and add these 2 fractions together, and I am telling you, you will get L over y quantity L minus y. Okay, so I've just spent quite a bit of time just dealing with this side over here. So now I can rewrite this side over here as the integral of 1 over y plus 1 over L minus y dy equals kt plus c. I've already integrated the right-hand side. Okay, so now we can integrate the left-hand side, and we integrate that. We're going to get the natural log of y minus the natural log of L minus y, that's a y here, equals kt plus c. Now I'm going to stop here for just a second, and I'm going to this isn't the answer, but we're getting there. I'm going to clean this up. I want to point out where this negative came from. You might think, Mr. Allen, shouldn't that be plus ln, absolute value of L minus y? And it seems like it should be, but the problem is think about how the chain rule works for differentiation. If we did the derivative of this and it had been like 2 minus x, then by the chain rule, you would have ended up with a negative 1 when you do the chain rule, right? So the same thing happens for integration. Since this variable is negative, when you integrate this, you have to then account for that negative. Okay, so I'm going to go ahead and go to the next slide. And I'm going to write what we have from the previous slide. Let's go ahead and start doing this in red. So we have the natural log of y minus the natural log of L minus y equals, I think it was kt plus c. So that's where we left off on the other side. Now I'm going to do some log rules. And you know what? Before I do the log rule, let's do this. Let's change that negative to a plus, which makes this negative. It makes k negative, but it's not going to change the sign of c. Now you might say, well, Mr. Allen, k is a constant. Why does that have to change? Well, k is going to be a constant that's dependent on the model that we're looking at. This c, constant integration, the constant of integration c, that does not matter. So it actually isn't going to change that. Now, if you want to write minus c there, you can. I'm not. But I am going to put the minus with the k. So then that's going to give us the following. It's going to give us, and I'm going to use a log rule now for this side over here. This is going to be the natural log of L minus y over y, absolute value, equals negative kt plus c. Now I'm going to get rid of the natural log by doing e on both sides. So I'm raising both sides with a base of e. That's going to give me absolute value of L minus y over y equals ce to the negative kt. I hope you remember this step on the right from when we did section 5.2 from last year. If you don't remember, I would encourage you to ask me or look back at your notes. But anyways, that's what that becomes. Okay, so we got to get rid of the absolute value symbols. So when I get rid of the absolute value symbols, that really doesn't do anything to c, because remember, c is an arbitrary constant that can be determined by the problem. Now I want to get rid of the y's here. So let's just cross multiply here. So we would get, let's see here, that'd be L minus y equals y times c e to the negative kt. Okay, so let's go ahead and add y to the other side. So then this would be L equals y plus y c e to the kt, and there's a negative there. L would be equal to, I can factor out that y. This is a really long problem, and I realize that. It's kind of interesting, and it might feel like, Mr. Allen, why are you doing this way? Just trust me, you'll see. I'm almost there now. Now remember, our goal, if we go back to the last slide, our goal is to solve this differential equation. We're almost there. All I've got to do is get y by itself, which now I can do. Y, I'm just going to divide all of this stuff in the parentheses over L over 1 plus c e to the negative kt. That's the general solution. This is the general solution for that logistics differential equation. That's the general solution. Now, the only thing that's going to look different when I go to the next slide is instead of this c being c, they use a lowercase b, but it's the same thing. So let's go ahead and move on. Okay, so here's the general solution that I just mentioned, and you'll notice that in our book they use a b there instead of c, and I'll be honest, I'm not sure why they use b. Now, if you were to graph this general solution, which by the way would have infinitely many solutions, the curve in general will look like this curve here, this black curve, this logistics curve. Notice that y equals L, that's the carrying capacity. Now, some things that you want to consider when you're dealing with this logistics equation, and I'll bring them up. Okay, we already know what L is, right? That's going to be a horizontal asymptote, right? That's a horizontal asymptote. So I guess a question I have for you, I got a couple of comments, I guess, or questions I'll pose to you that I'm not going to go over in this video. First of all, T clearly is time, right? T is time. L is the carrying capacity. My questions are, number one, what does B do? What does B do to the curve? When you change B, how does it change the curve? And number two, what does K do to the curve? So I would encourage you, if you are really interested in this, and this is a very useful application of differential equations, is to figure out how those variables, or I should say constants, affect the shape of this curve. All right, so let's go ahead and do our second and final example. The first example was just me deriving the formula, and that's an application. And it says a state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. The growth rate of the elk population, P, is given by the following differential equation, which should look very familiar. This is the logistics differential equation that we just solved, where P is between 40 and 4,000, and T is the number of years. So question one, or question A, is write the model for the elk population. That's where we'll spend the most of our time. Then we'll graph it. Then we'll use the model to predict the population after 15 years. And finally, we'll find the limit of the model. And that's as T goes to infinity. So let's go ahead and do A. Let's find the model. So remember our solution, our general solution is Y equals, we have L on the top, 1 plus BE to the negative KT. This is our general solution, that's a B. So what I'm going to use first to get this problem rolling is I'm going to use the fact that at T equals 0, if you will, that there are 40 elk. So that was the initial population, and we're going to use that in the problem here, and I'll go ahead and do this. Let's just go and do this in green. So we're going to get 40 for Y, that's the number of elk. Oh, and I should note that L is 4,000. I probably should have mentioned that. It was given in the previous slide right here. We know that they believe that no more than 4,000 elk. So that's kind of an assumed thing. Over 1 plus B e to the negative k, and then times 0. Now, timesing anything by 0 is 0. So that's going to give us the equation 4,000 over 1 plus b, because e to the 0 is just 1. So I've got 40 on the left and 4,000 over 1 plus b on the right. So when we cross multiply here, we'll get 1 plus b is equal to 100, and b then is 99. So in this particular problem, we know that the b value is 99. In other words, we know, and I'll go ahead and write this back in blue, we've taken a step. We've got one more piece of information here. We know already that L is 4,000, and we now know that b is 99. Now the next thing we're going to have to figure out is what this k value is. Okay, t is time, so that's variable. We got to find the k value. How are we going to do that? Well, if we go back and look at the problem, we knew that initially there was 40 elk, but we also are given that right here that the number of elk after 5 years is 104. So we can use that now. So let's go ahead and write that as 5, 104. And we'll do this step in green. So that tells us that Y will be 104. L is still 4,000 because that's the carrying capacity, over 1 plus 99. We figured out B in the last step. E to the negative K, and then T here is, I think we said 5. Yes, it's 5. So now we need to solve this. So we could again cross multiply here. So we're going to get 104 times 1 plus 99 e to the negative 5k equals 4,000. Running out of room here. So we could divide both sides by 104, and then we would minus 1, and then we would divide by 99, all that good stuff. And I'm not going to do the rest of this step. I'll let you do that. And it turns out that K, and I've got my calculator here, I've already figured this out, K turns out to be 0.194361. I'm only going to go out this many decimal places for this problem for right now because that's not the final answer. I actually stored the whole decimal in my calculator, but I would encourage you to check that the K value that solves this equation is that value. Just check that you can do it, because if you can't get from here to here, then it's going to be very difficult for you to solve problems on your own. All right, so now that tells us the answer to question A is y equals 4,000 over 1 plus 99 e to the negative 0.194, and I'm going to abbreviate it here, t. Now don't forget the negative there. There is a negative in front of this, so we need the negative. So there's our answer for question A. This is the model now that we can use to answer the rest of the questions. So question A is done. Now question B I've actually already done ahead of time, and I've got it all pasted here already. So here was our, using our graphing utility, you can graph the slope field if we wanted to do that, which would be these blue things. But the slope field, by the way, is based on the differential equation, correct? So that's what that is. That's not the solution we got on the last slide. The last slide, this is the solution, the particular solution for our problem. I should maybe write that. This is the particular solution, not the general solution. The general solution would be here. This is the particular solution. Now this pink curve, that is the equation that I just said is the particular solution. So there's the graph of that. Notice that this is going from 0 to 80 for the t values and 0 to 5,000 for the y values. Question C says to estimate the elk after 15 years. So now what we're going to do is we're going to say y equals 4,000 over 1 plus 99 e to the negative, make sure I say that correctly again, e to the negative 0.194361, and then here t is going to be 15, and I'm going to extend my division bar here a little bit further. So we're trying to, so now we can use our solution to estimate the population after 15 years. And again, I've already done that. And when you work this out, you will get 628.538, that's a 5, elk. So I'm just going to say that that's about, I would estimate about 629 elk at year 15. And then our very last question, oops, I kind of went over that, is what is going to be the limit? What is going to be the limit as t goes to infinity of, and I'm going to call this f of t, if that's okay with you, just so I don't have to write it again. What is going to be the limit of f of t for this particular problem? Well, we could work this out by hand, or we could just use the fact that we already know what that is going to be. What is this horizontal asymptote in this problem? Well, I think we established that that was 4,000 because that was the carrying capacity. So question D, the answer is 4,000. In other words, in the long run, the number of elk that this can support is 4,000. So that was a very long video. We did 2 examples, but hopefully that was good, and we'll stop it there.